Changing scales in scale drawings. This is lesson 10. We're going to explore different scale drawings of the same actual thing. So our ICANs, given a scale drawing, I can create another scale drawings that shows the same thing at a different scale. You can use a scale drawing to find actual areas. So you get your ICANs, today's date, and page number, and you're ready to move on. Okay, let's do some measurement stuff here. So estimate the size of your foot in centimeters or inches. Well, for most of you, it's going to be less than 12 inches for a foot, even though that's where we get the term foot for. But most of you haven't gotten to your full height yet, so you're likely not very close to a foot. And it just depends on a lot of things. That's why the term foot can be a little subjective. If a student uses a ruler like this to measure the length of their foot, which choices would be appropriate measurements? Well, the ones that are going to make the most sense if we use this are going to be probably not the 9 and 5/64 inches, right? Because here's the inches side. What are these broken up into? Yeah, eighths, right? Because we have 7 marks in between each one, so that makes eighths. So we could use this one. This one's going to be a bit rough. What about to this exacting decimal place? Yeah, not gonna fly. We can definitely get to a halfway point in between, right? And it looks like we have 10 in between here, so we're probably not going to be able to do 2 places to the right, because that would make a total of 100 parts in between, and that would be pretty rough for us to get that small of detail on here. So there's really only 2 that are going to be ones that we could probably use in this situation. All right, we're going to look at the same plot and kind of talk a little bit about the drawings. If we were in class, we would do this a little bit more together, so that way we could all look at it. But this is a triangular piece of land that is in Philadelphia. In real life, it's 90 meters by 120 meters. And if we look here, you can tell that this is definitely not 90 meters that I have on the screen here, right? It's much smaller than that. So depending on the scale, we could have all kinds of different ways that this is being made. We can probably guess that this is somewhere around an inch. So it could be 1 inch to 90 meters. It could be something else. Obviously, it just kind of depends on how we measured it out. But it's clearly centimeters or inches that are being used for the scaled drawing of it. Likely centimeters, since that would give us a much more easy, accurate picture to look at. Okay, so if we were in class, everybody would have gotten one of these different ones to try and draw out. So how does a change in scale affect the drawing? Well, in every one of them, we're using 1 centimeter, right? But if you look, that 1 centimeter represents different distances. The more that it represents, the smaller those pictures get, right? Here we have each one of these centimeters is 50 meters. Well, it's 120 meters across the bottom part of the base part of that triangle. So you can see that that's clearly a very small version. Whereas here we have 1 centimeter equaling 10 meters, and each one of these lines, if it was blown up to an actual centimeter, you would see that it takes up several of those. So how do the lengths compare, within the different ones? Like, how does this 1 centimeter to 5 meters compare to the 1 centimeter to 15 meters? If you said that this is 1/3 the size of this, then you'd be correct, because look, here, the original was 120 meters. And so we have 1, 2, 3, 4, 5, 6, 7, 8 to approximate that 120 meters. It's a little bit off just because I can't see the exact spot on here. But just by even using a partial like that, we can see that we've only got a few here. We count this over here, and we're going to see that we have 3 times as many. Well, why does that work? Well, it's because we have this is 15 meters here, and these are representing each one 5 meters. So it takes 3 times as many here to represent the same amount of distance here. So for 1 centimeter here being 15, it takes 3 centimeters here to represent the same 15. So likewise, when you're going from this to this drawing, it's multiplying by 1/3. And the same thing happens when we go from this really small one to here, right? What's the scale factor difference between this 1 centimeter to 5 meters and 1 centimeter to 50 meters? Yeah, each one of the ones here is representing 10 times the distance every one of them here is. So for every 10 here, I just have 1 here. Now, obviously, that's not the scale factor between those, because we are talking about the 1 centimeter in each case being equal to a different thing. But it's that representation that changes based on how those look. What about the area? How does that change? It's a little bit different. It's not going to be just 3 times if we're looking at comparing these together. Because think about it. We're multiplying the one side by 3, and we're multiplying the other side by 3, right? So this is actually going to have 9 times the area that this one has. Wait, why does that happen? Well, think about it. You've got this being increased by a factor of 3. This is being increased by a factor of 3 as far as the space that it covers. So if you've got 3 times the 3, then that is going to give you that 9 times as much as what it would have been in this situation. What about this compared to this? How is that space, that area, going to compare? Well, you should have said 100 times, right? Because to go from this 50 to this 5, we've got 10 times as many that we do here. And you can almost see that it is 100 times bigger than this, because this looks like it's slightly over 2. This looks like it would be a lot closer to 200 as far as its entire spacing there. Because look, if we enclose that, that would be about 4. It's half of 4, so it would be right around 2. Same thing here. Obviously, it would be a lot easier to be more accurate with this space here. But it's still the same sort of concept in there. So as the number of meters represented by 1 centimeter increases, the lengths of the scale of drawing decrease. And as the number of meters represented by 1 centimeter increases, the area of the scale drawing also decreases, but it also decreases the area by the square factor of those lengths. In other words, if I'm going from here to here, I'm multiplying by 1/10, right? Well, it's actually going to be 1/10 squared, 1/10 times 1/10, so it's 1/100th the area here, which makes sense because we said back the opposite way, this would be 100 times as much. Could draw this out if you had a chance, but don't have to. So the scale for this is 1 centimeter to 30 meters. you would draw a new scale drawing of 1 centimeter to 20 meters. Is your new drawing going to be smaller or larger? Yeah, it should be larger, right? Because now we've got this 1 centimeter representing a smaller length, so we need more centimeters to show the same distance that we have here. So it just really kind of depends on, again, that piece that you have that you're using with it and how much each of those centimeters are representing. The bigger number that it's representing, the smaller it's going to make it. Whereas the smaller the number, the bigger it's going to make the drawing. So sometimes we have a scale drawing and want to reproduce it and at a different scale. Two common ways to do this. We use the original scale drawing to calculate the actual lengths, and then using the actual lengths and the new scale to calculate the corresponding lengths. So in other words, going from the drawing back to what the actual lengths were, and then refiguring all those new scaled lengths, or scaling lengths in the original scale drawing by a factor that relates to the scales to the two drawings. So kind of like what we talked about before with the different triangles and how you had to change each of the parts by multiplying by 10 or multiplying by 3. If you have a map that uses a scale of 1 to 200 meters, you draw a new map with the same of the same place that is 1 centimeter to 20 meters. How is that going to compare? Yeah, the lengths are going to be 10 times as long, but the area is going to be 100 times as large. Think back to the triangles we were talking about. The one that had the 1 centimeter to 50 meters as compared to the 1 centimeter to 5 meters. It was 10 times the difference. And then it was because of that, because both the parts that you would find with the area are 10 times as much, then you have to multiply those together and you get 100 times the area. Suppose you have a map uses a scale of 1 centimeter to 200 meters. If you did it to the 1 centimeter to 20 meters, 1 square centimeter is going to actually represent 400 centimeters. Why? Because if each of the sides of that square are 1 centimeter by 1 centimeter, that's representing a 20 meter by 20 meter square. So that 20 meters times 20 meters gets you 400. So how much area did the actual 1 centimeter on your original map represent? Well, so here on the previous one, that was 400 centimeter or 400 square meters represented by 1 square centimeter when you talked about it as 20 meters. Here we want to go back to that original 200. So how much is it? Yeah, 40,000 square meters. Why? Because we're talking about 200 meters by 200 meters. So now you've got one tiny little square centimeter representing 40,000 square meters. And that's, part of the reason. And it just, depends. Like, how portable do you want the map? I mean, you don't want to carry a map of the city of Fayetteville around that's actual size. You've got to think about that trade-off of what's important with the scale and the scope of it. So we are done with our ICANN, or what we were working on, and our ICANNs should be down. We should be good to go. Thanks for watching.